Physics 1, Lab 1, Constant Velocity. Today, we conducted an experiment to observe an object at a constant velocity, which means same speed and direction. In my case, I rolled a water bottle across a carpeted floor. Some of the important concepts that we used in this lab is Newton's first law, which states that an object in motion stays in motion, and an object at rest tends to stay at rest unless acted on by an external force. In our model, there was external forces like gravity, but we also coded a model to show how the velocity compares without any external forces. In this experiment, we used the position update formula and the velocity update formula, as well as Newton's second law, which states that net force is proportional to change in momentum. And change in momentum is equal to mass times change in velocity. So net force and velocity are intertwined. The purpose of this lab was to observe the actual motion of a water bottle rolling across the floor and compare it to a computational model or the predicted motion. So the results of this lab showed that in the real video or the tracker, the water's velocity changes. It starts small, peaks, and then goes back down a little bit and eventually stops. While in the computational model, the velocity stays consistent throughout. And this is once again because in real life, there are external forces such as friction, which causes the net force to be non-zero, thus making the velocity change. So this is a position versus time graph of the computational and real life model. And as you can see, the real life model is moving at a quicker rate than the computational model. And this can be seen in the slope. Change in position over change in time equals velocity. So the velocity is steeper in the real life model. However, if this graph were to continue, eventually you would see that the position plateaus and as the time continues, and the slope will generally start to decrease, while the computational model would just keep going. And that is because, once again, there is net force causing the velocity to change in real life, but not on the computer. So this is our predicted motion model, which was coded and shows it without any net force. This is to simulate the start and stop of the video, so it only goes a little bit. The video only goes for a certain time, but it shows that the ball will continue to go to consistent velocity. And next, here is the video of the water bottle rolling across the floor. As you can see here, this is my x-axis, the line that the water bottle rolls across, and then this is the y-axis. And on the right here, I have included the velocity in the x direction, which, as you can see, it starts at 0.6, goes up to 1.026, and then goes back down to 0.674, which shows that the velocity is continuously changing with each time frame. So here are some of our relevant questions. If I were to change the positive and negative x direction, the only thing that would change is the magnitude. If I were to make my x-axis negative on the right side instead of the left side, I'd still have the same speed, but we'd put a negative in front because it is rolling in the negative x direction, or the opposite r hat direction. Is it possible for you to say how many pushes or pulls are added together to give zero net force in the case that you observed? So in the computational model, the net force adds up to 0 because the velocity is continuous. So we can know that there is only 2 forces acting on our water bottle in the computational model. That would be gravity and the force from the carpet onto the water bottle. And we know this because there is no change in velocity in the y-axis. It's just in the x-axis. And since the x velocity is continuously the same amount, then there is no external forces. However, for our real-life model, we can see that the water bottle starts to slow down. So there's still gravity and the force from the floor onto the bottle, but there's also a force from my hand pushing the bottle, and to stop the water bottle, there's friction. If the water bottle continued to move without stopping, we would say that friction is non-existent or not important. And if it were at 0 and it didn't move, we'd also say that the net force is 0. So thank you for watching, and I hope you have a great day.